Okay, today we're going to cover stuff in both 5B and 5C. We'll see how far we get, but I'll sort of bounce around a little bit because I think there's sort of two parallel topics, upper triangular and diagonal matrices. Okay, so we're going to talk about matrices, obviously. So just recall that when T is a linear map from V to W, and V and W are finite dimensional with fixed choice of basis, then we can represent this linear map with a matrix. So this is a matrix that uses all this data, right? So this matrix represents the linear map T in terms of the fixed choice of basis for V and W. Okay, and remember, if the dimension of V is say n, and if the dimension of W is say m, then this matrix will be an m by n matrix. It will have m rows and n columns. Okay, but right now what we've been talking about is operators. And an operator is just a linear map from a vector space to itself. So if T is an operator, well, if I want to talk about its matrix, I mean, it only applies to the case when V is finite dimensional. And V is finite dimensional with a fixed choice of basis. And I can still talk about this matrix M of T. But of course, since the domain and the codomain are the same here, that will mean that M of T will be an n by n matrix. So it'll be a square matrix. Okay, note that the convention here is that we just choose, if we're going from V to V, we just choose a basis of V to be the same as in the domain and the codomain, almost always, right? So by convention, choose the same one. In the domain and the codomain. I'm trying to think if there's any situation in which you want to choose different bases. I mean, of course, that definition will make sense. It'll probably be a bit confusing. I can't currently think of a situation in which you'd want to pick different bases, but in principle, you could. But our convention will be, unless I say otherwise, we're going to assume that all matrices are written with respect to some fixed basis that's the basis of both the domain and the codomain. Okay, so this definition is not a new definition, but it's not so bad to state a definition more than once. So here we have an operator T on a n-dimensional vector space V, then the matrix of T this is M of T, A11. Remember, the first index almost always refers to which row you're in. The second index always refers to which column you're in. Where the entries A, J, K are defined by, okay, and as always the case, the kth column tells you about what T does to the kth basis vector, right? So somewhere in here we have the kth column. I guess that will look like A1K, A2K, ANK. So this kth column will tell you that T of VK is equal to A1K V1 plus A2K V2 plus ANK Vn. Now, the kth column tells you how to write T of VK in terms of the basis. And here, I'm making this definition. In making this definition, I'm already assuming that I'm using the same basis for V as both the domain and the codomain. Okay, so nothing here is new, but that doesn't mean it's not worth saying. And of course, convention, if V equals Fn and no basis is specified, you assume you use the standard basis. Okay, the point being, we're talking about operators, so we'll talk about square matrices. Okay, so some terms for square matrices, which hopefully you've seen before. The diagonal, sometimes called the main diagonal of a square matrix, consists of the entries A, I, right? So A11, A22, A33, that's along the line from the top left to the bottom right. These entries, you would say that these entries are along the main diagonal. Okay, the reason that we use the word, sometimes you say the word main diagonal, is because sometimes the line going from the bottom left to the top right, sometimes that's called the anti-diagonal or secondary diagonal. So I will sometimes say main diagonal just out of habit. A matrix is called upper triangular if all entries below the main diagonal equal 0. And it's called lower triangular if all the entries below or above the main diagonal are equal to 0. Okay, so that upper triangular matrix looks like this, right? So you have the main diagonal, A and N, or yep. Upper triangular says that everything below here is 0. So everything here is all 0. Everything above could be anything. So it's this triangle, right? It's upper triangular. All the non-zero entries live in this upper triangle, and lower triangular has anything here and zeros here. Okay, of course, some of these anythings, some of the elements on the diagonal could be 0, but all we're saying is that below or above the diagonal, you only have 0. Okay, and a matrix is called just diagonal. That's as an adjective. If its only non-zero entries occur along the diagonal. Okay, so as I sort of stated at the beginning of this definition, all these definitions traditionally are only made for square matrices. That way you can talk about, I mean, this picture that I've drawn implicitly, I'm drawing square matrices everywhere. Right, so of course, diagonal means that you only have things here. So this is the same thing as saying that a matrix is diagonal. That means that it's both upper and lower triangular. Okay. So what's the point here? There's a key idea, which is one that's sort of explored a little bit in 308, but it's hard to find the time to do everything you want in 308. The idea is this: for every operator, in fact, every matrix, but for every operator, if you choose different bases of the vector space, and so you choose one basis, you'll get one matrix. You choose another basis, you'll get a different matrix. You choose another basis, you get a different matrix. All these different matrices correspond to the same linear map, just thought of with respect to a different basis. So a very key idea in linear algebra, in machine learning and data science and statistics, whatever, is to choose a basis of the vector space that gives you a nice matrix. This is like a very fundamental idea. So idea, as you change the basis of V and keep the operator fixed, this matrix changes, right? Because everything is written with respect to the basis that you choose. So the idea is to choose a basis so that the matrix is nice. Normally, we're used to thinking of Rn just in terms of standard basis, and therefore we're sort of stuck with the matrix of a linear map. But that's somehow, it seems easier, but it's a very powerful idea to try to change the basis, go to a different basis. All bases are sort of equally good, but if you have a nice matrix, then you can see some cool things from the matrix. So actually, this is really what's happening when you diagonalize a matrix, which you all learned how to do in Math 308. So we say a linear operator on V is diagonalizable if there exists a basis of V such that M of T is diagonal with respect to this basis. That's what it means to diagonalize a matrix. It's not that clear when you learn it in 308, I think, because you sort of have to combine the section you learn on change of basis matrices with the section that you learn about diagonalization, and then think carefully about it. But diagonalizing a matrix is really choosing a basis of the vector space so that the matrix of the linear operator is a diagonal matrix. Okay, so now let's motivate. So imagine that V is an eigenvector of T with eigenvalue lambda. Okay, and imagine that you choose a basis of V that starts with this little v, the eigenvector. Imagine that B is a basis, starts with V, and there's something is your basis for V. Right? We know that we can actually start any basis with any linearly independent set of vectors, which means V is an eigenvector. That means it's non-zero. So you can start the basis with V if you want. What does this say about the matrix? Well, the first column of M of T, you get that by seeing what T does to the first basis vector. So the first column here is given by T of V. That's the first basis vector. You have to know what T of V is in terms of the basis of the vector space. Well, V is an eigenvector with eigenvalue lambda. This is lambda V, which means that if you write it in terms of this basis B, we've actually already done it, right? It's lambda V plus 0 times the second basis vector plus 0 times the third basis vector. This says that the first column is exactly lambda 0, 0 down to 0. That's the first column of the matrix if you have an eigenvector as the first vector in the basis. Similarly, if you got a different eigenvector, now W is a different eigenvector. Maybe I should say not a scalar multiple. So it's an eigenvector which is linearly independent, so not a scalar multiple of V. And let's suppose that it has eigenvalue mu. It may or may not be the same as lambda. Well then, our basis will now go VW dot dot dot. So the second column of the matrix is given by T of W, which is of course mu W, which is 0V plus mu W plus 0 of the third basis vector plus 0 of the fourth basis vector, etc. Which says that the second column of our matrix is going to be given by 0, mu, 0, 0. So maybe I should say first and second column, R. So if you could continue this process and just choose a linearly independent eigenvector each time, then you would get that the matrix would be diagonal. Right? The diagonalness of this matrix basically exactly says that each basis vector gets sent to a multiple of itself under the linear operator. And if you remember back to 308, that's exactly the condition that you need for a matrix to be diagonalizable. You need to be able to find an eigenbasis of the vector space. So this proof, I mean, this is basically a proof. Let's call this a pre-proof of the theorem that I'm about to write down. It's the following theorem. Suppose that T is a linear operator on V, and V1 through Vn is a basis of V. Then the following are equivalent. 1, the matrix of T with respect to this basis is diagonal. That's exactly the same thing as saying that Vj is an eigenvector for all j. Okay, so this pre-proof shows that if you have a basis, well, okay, you need to combine this with induction, I guess. But you do induction. Maybe you can even just do it all at once, right? So if you have an eigenvector, for each of your basis elements is an eigenvector, then you'll get that the matrix is diagonal basically by definition. Okay, so the pre-proof proved that 2 implies 1, essentially. On the other hand, if, right, so you need to know 1 implies 2. So if M of T is diagonal, so let's say lambda 1, lambda 2 to lambda n, well then the definition of this matrix, it tells you, each column tells you what it does to it, what T does to a basis vector. Right, so by definition, then, of the matrix, T of Vj is just given by the jth column. What is the jth column? It's 0, 0. There's a lambda j in the jth slot. 0, 0 Vn. Which is exactly saying that T of Vj is lambda j Vj. Which means that Vj is an eigenvector of T. And this is true for all j. So hopefully this is ringing some bells, but I think when you first learn about diagonalization in Math 308, it's a little bit hard to see what you're really doing. And it's probably still a little bit hard now, even as you're taking Math 340. It's something you have to think about. In Math 308, it sort of just seems like this algorithmic process that gives you like A equals PD P inverse, if you remember that. And you ask like, well, why the heck would I want to write A as PD P inverse? The real point is that the P and the P inverse were change of basis matrices, which changed you to a basis of eigenvectors. So the matrix of the linear map was a diagonal matrix. So now when you see, when you think about diagonalization, what you're thinking about is changing the basis of V to make the matrix of T nice. Okay, but as you may remember, not every operator is diagonalizable, even over C. So remark. In other words, sometimes you just don't have a basis of eigenvectors. Not every linear operator is diagonalizable. And then you might think, well, okay, we saw that over R, you might not have any eigenvalues, but over C, you always have an eigenvalue, which means that actually you always have, counting with multiplicity, you always have n eigenvalues. But even over C, where you're guaranteed to have an eigenvalue, your linear operator still may not be diagonalizable. There's actually just a nice, pretty elementary example. So let's let T be the linear map from C2 to C2, given by T of xy equals 0x. Let's try to figure out what possible eigenvalues T can have. Okay, so you could do this by writing down the matrix of T with respect to the standard basis, and then computing the characteristic polynomial as you did in Math 308, finding its roots. But we haven't covered determinants, right? So this we can just analyze by hand. Okay, so suppose that V is an eigenvector. With eigenvalue lambda. Okay, what does this mean? This means that T of V will have to be lambda V, which means that also if you do T twice, T squared of V, you better get lambda squared of V. Because what you're doing is you're going to scale by lambda twice. But T squared of V, that's T squared of V1, V2. What is T of V1, V2? Well, what T does is it sends you to 0, comma, the first coordinate. Right, T sort of just shifts to the right. And then this will be 0, 0. That's what T does to the vector 0, 0, V1. So what this says is that this is supposed to be lambda squared of V1, V2. And remember, I was assuming that V is an eigenvector, so V is not the 0 vector. So it's a non-zero vector, but when you scale it, you get 0. That must mean that the scalar is 0. Okay, so what this shows is that 0 is the only possible eigenvalue of T. So now we can look for some eigenvectors, right? We actually knew that there had to be an eigenvalue. What this says is that the only eigenvalue is 0. If we were to do the Math 308 computation, you would see that the characteristic polynomial of this matrix is like lambda squared, or negative lambda squared. It has 0 as a root twice. Okay, so what are the eigenvectors? Right, in other words, I want to know E of 0t, this eigenspace. That's defined to be the null space of T minus 0i, which is just the null space of T. Okay, but what vectors does T send to 0? the only thing, the vectors that t sends to 0 are vectors that look like 0, comma, anything. Right? Because from the output, the first coordinate needs to be 0 in order to get 0, 0. So this is just the span of the vector 0, 1. Which means that this eigenspace is one-dimensional. So the most number of linearly independent eigenvectors of t that I can get is just 1. So I can't find a basis of eigenvectors of C2, which means that t is not diagonalizable. It's one-dimensional. So there does not exist a basis of eigenvectors of t, which means that t is not diagonalizable. Right? That's what the proposition we just proved shows. Okay, so in other words, diagonalization is just finding a basis so that your matrix has a very nice form, but it's asking for too much. When you can diagonalize a matrix, it's great, but you can't always do it. It's asking for too strong a property. Now, of course, if you can do it, it's good to do it for various reasons. Principal component analysis is maybe one of the most useful things related to diagonalization. It's not, you can phrase it in terms of diagonalization of something, but so if you took 380, I mean, singular value decomposition you can accomplish by doing diagonalization of like A transpose A and then some tricks. The idea is essentially the same though. Okay, of course, we can state now some easy results about when, or at least one easy result about when you know that a matrix or a linear operator is diagonalizable. It's a pretty quick proof. Okay, so suppose that V is a vector space of dimension n, then if T has n distinct eigenvalues, then T is diagonalizable. So maybe I'll just say the proof. It's like 3 sentences in the notes. If T has n distinct eigenvalues, that means that you can get n linearly independent eigenvectors, because eigenvectors corresponding to distinct eigenvalues are linearly independent. We proved that. But if you have n linearly independent vectors, they must be a basis. So in this case, you can form a basis of eigenvectors. Then by the previous result, that means that T is diagonalizable. So if you know that you have enough different eigenvalues, you can definitely diagonalize, right? That is something that failed in this example. In this example, T only had a single eigenvalue. But if T happened to have 2 eigenvalues, you would know it must be diagonalizable because you can just take the two eigenvectors. Okay, but I want to shift our focus now to a weaker property, because diagonalizability is a very strong property. Well, go back to the definitions we made earlier today. Being a diagonal matrix is a very strong thing. Slightly weaker is being an upper triangular matrix. So you could make, you could ask the question, well, what does it mean to say that I can choose a basis so that the matrix of my linear operator is upper triangular? And can I always do it? Right, because a diagonal matrix is more specific than an upper triangular matrix. So this process of diagonalization is giving you something even stronger than being upper triangular. So what if we weaken it to just asking for something to be upper triangular? So here's the result. So suppose that T is a linear operator on V, and V has a basis consisting of these n vectors. Then the following are equivalent. So 1, the thing that I'm interested in, the matrix of T with respect to the basis is upper triangular. Upper triangular. Okay, 2 is that TVJ is in the span of the first J basis vectors for all J. And 3 is that the span of V1 through Vj is invariant under T. It's an invariant subspace of T for all J. So this is telling you exactly what it means to say that the matrix of a linear operator is upper triangular. It means any of these other two equivalent conditions. Either it's saying that when you take T of any of your basis vectors, you end up in the span of all the basis vectors up until that one. Or it's saying that these spans of consecutive basis vectors are invariant under the linear transformation. Okay, so let's see why this is true. Hopefully, you can sort of see why 1 is equivalent to 2 based on our definition of diagonal, like this, the diagonal version of this theorem. Of course, we'll talk about it, but hopefully you're sort of already thinking about it. So 1 equivalent to 2 is basically by the definition of M of T. Right, remember, the jth column of M of T is supposed to be giving you the information of T of Vj. Right, so the jth column here tells you about T of Vj. Right, so if the matrix is upper triangular, that means it lives in this triangle. If you look at the jth column, you have all not, or a bunch of entries, and then below the diagonal, zeros. Right, so I guess I can be specific. This is A1J, A2J, down to AJJ. So this jth column tells you that T of Vj equals A1J V1 plus A2J V2 plus AJJ Vj. But then you have only zeros after that. Again, the jth column of the matrix tells you how to write T of Vj in terms of the basis. So to say that you're 0 below the diagonal just means that the coefficients are 0 after this point. But this is exactly saying that T of Vj is in the span of the first J of the basis vectors. Conversely, if for each Vj, you can write T of Vj in terms of just the first J basis vectors, and you write down the definition, by definition, the matrix that you get, that matrix will only populate the upper right triangle of the matrix. Okay, so this is really just by the definition of the matrix of the linear map. So I only need to show the equivalence of these two things. Okay, so let me do something really fancy here. Amazing. Let me go on to a new page, but paste this. I can even change the color of this, I think. Yeah, amazing. Change it to some shade of blue just to show that this isn't part of our thing, but this is just something I'm carrying over from the last slide. Still need to show two implies two if and only if three. Okay, so suppose that 3 holds. So let's actually just say I'm going to prove 3 implies 2 for now. So if for all j, the span of the first j basis vectors is invariant under T, this means that every vector in here stays in here when you apply T. In particular, T of Vj, which is a vector in this subspace. I mean, Vj is a vector in the subspace. So when you apply T, this has to stay in the subspace. But that's exactly the second condition. So maybe I should say then for all j, T of Vj is in the span. Right, so 3 implies 2 is you just write down the definition of what it means for these spans of consecutive vectors to be invariant under T. So now 2 implies 3. So suppose that T of Vj is in the span of V1 up through Vj for all j. I want to show that T, or for any k, this is invariant under T. Okay, well, let's think about where do the spans, what happens to the elements of these spans under T? Okay, well, what is T of V1? I'm assuming 2, right? So I'm assuming that T of V1 ends up in span V1. But span V1 is certainly a subset of span V1 up through Vk. In other words, if I take V1 and apply T, V1 living in this subspace, and I apply T, I end up back in the subspace. Similarly, T of V2. But since I'm assuming part 2, this is in the span of V1 and V2. But that's also a subset of the span V1 up through Vk. Then you keep going down to T of Vk. This is, since I'm assuming part 2, in the span of V1 up through Vk. So what this says is if you take any V1 up through Vk, you apply T, you end up in this subspace. So now let V be a vector, any vector you want in this subspace that we're trying to show is invariant. So let V be any vector in here. Then V is A1 V1 plus A2 V2 up through AK VK, because it's in the span of those things. So then T of V, I'm trying to show that T of V ends up in the same subspace, but T of V is A1 T of V1 plus A2 T of V2 up through AK T of VK. And now, by assumption, each of these vectors is in this subspace. So I'm taking a linear combination of vectors in the subspace. That means that T of V is in fact in the span of these k basis vectors. So what I've just shown is that you take any vector in here, you apply T, you end up back in there. That means that that subspace is invariant under T. And since k was arbitrary, that holds for all k. I use a different letter here so as to not be confused about what we were assuming versus what we're trying to prove. But that shows that as long as each Vj is in the span of the first j basis vectors, that every time we take the span of the first j basis vectors, that's an invariant subspace, which is what we wanted to show. Okay, so to be diagonalizable has like a very clean interpretation. It just means that you have a basis of eigenvectors. To say that you're, I guess we could call this upper triangularizable, or in other words, to say that your matrix with respect to the basis is an upper triangular matrix is saying something a little bit less clean. It's saying that either each basis vector ends up in the span of all the previous ones, including itself, or it's saying that as you take these consecutive subspaces, because consecutive spans, you always get invariant subspaces of T. So the question is, this is a weaker property than being diagonalizable. You're not always diagonalizable. Are you always upper triangularizable? Of course, the only reason I'm asking that question is because the answer is yes, right? Which is, I'll call this a theorem. So suppose the V is a finite dimensional vector space over C. Okay, so here, this actually is important. I'm going to need to take a bunch of eigenvalues, which I can't always do over R, but you can always do over C. So this is an example of one of these theorems that's true over C and not necessarily true over R. And suppose that T is an operator on V, then T has an upper triangular matrix with respect to some basis of V. Okay, so the equivalent, the analogous diagonal matrix statement is false, as we showed by that example. But you can always choose a basis such that T is upper triangular. Okay, and this we can prove by induction. So what we'll do is we'll induct on the dimension of the vector space. Dimension of V. Okay, so if V is one dimensional, right, this is our base case, then V is just the span of a single non-zero vector. And T is an operator on V, right? So T takes V to something in V, which means that it's some lambda in V. Some lambda times V. Because that's what the space is. It's just the span of a single vector. Every vector in there is some scalar multiple of V. Right, so the matrix is just lambda. Another way to say this is just that every 1x1 matrix is already upper triangular because it doesn't have any non-diagonal entries. Right? So the base case here, as often is the case, is just a trivial thing. Okay, now so suppose that dimension of V is strictly greater than 1, and assume that the theorem is true for all smaller dimensional vector spaces. The standard induction hypothesis. Okay, let T be an operator on V. I want to construct a basis of V such that T is diagonal with respect to that basis. Okay, but now, since T is a linear operator on a finite dimensional vector space over C, it has an eigenvalue. Here's where I'm using that our vector space is over C. So by a previous theorem, T has an eigenvalue. Let's call it lambda. Since lambda is an eigenvalue, this means that T minus lambda I is not invertible. Okay, so let's let U now be this range of T minus lambda I. Okay, so since t minus lambda I is not invertible, that means it has a non-trivial null space. It also means that, I mean, since it's from a vector space to itself, it means that t minus lambda I is not surjective. In other words, the dimension of u is strictly smaller. T is not invertible, it's not surjective. So here's where we're getting a smaller dimensional thing. And here's why we can now hope to apply the inductive hypothesis. Okay, so here's an important claim. U is invariant under T. Okay, so let's just do all of this claim in blue. So suppose that U is in U. I want to show that TU is in U, right? That's what it means for U to be invariant. But TU, I can write in a sort of a clever way as TU minus lambda U plus lambda U, which is T minus lambda I U plus lambda U. But now this vector is in U because U is the range of T minus lambda I. And since U is in U, lambda U, which is scalar multiple, is also in U. So both of these vectors are in U, which shows that if U is in U, then TU is in U. So U is invariant under T. Okay, well, what's the benefit of proving this claim? Well, remember, I'm trying to use the inductive hypothesis on this subspace U, which means I need an operator on U. But if I want to take the restriction of T and I want that to be an operator on U, I need U to be invariant under T. This is the whole point. So since U is invariant under T, T restricted to U is an operator on U. So what do I have? I have an operator on a smaller dimensional vector space. That means that the theorem holds. In other words, the restriction of T has an upper triangular matrix with respect to some basis of U by the induction hypothesis. So by the induction hypothesis, U has a basis. Let's say U1 up through UM, such that the matrix of T restricted to U, which is an operator, is upper triangular. Well, what does that mean? It means that by the previous theorem, it means that T of Uj is in the span of all the previous Ujs. Well, the restriction of T on Uj. But the restriction of T on Uj is the same thing as T of Uj. So T of Uj, since Uj is in U, you could just restrict. This is in the span of U1 up through Uj. That's what it means for this basis of U. Okay. We're almost there, promise. So I now have this nice basis, which we can extend to a basis of V. This was a theorem from a long time ago. We can extend this basis of U to a basis of V. Let's say, so we start with U1 up through UM, and then so we add V1 up through V n. This is now a basis of V, this guy. Okay, this will be our is this going to be a basis? Yeah, this will be our basis for which T is an upper triangular matrix. We're just going to use this proposition. And we know that for the U's already satisfy property 2. So I'm just interested in where T of V1, T of V2, T of V3, where they land. Okay, so this is the basis that we're interested in. Let me maybe circle in a different color. This will be our basis. So we already know that for the U's, they satisfy the property we want. If you take T of any of the U's, it ends up in the span of the first, like all the basis vectors up to that point. What about T of VK? Now for all K between 1 and n, T of VK is definitely T minus lambda I VK plus lambda VK. This is the same trick as before. But now what? This is in U. Which is equal to the span of the U's plus a scalar multiple of VK, which means that this is in the span of the U's and VK, which means that it's also in the span of the U's and the first K V's. So just by this little trick, I mean, choosing this T minus lambda I was kind of a very clever choice. But by this little trick, this blue circled basis has property 2 from the previous proposition. If you apply T to any of the vectors, it lives in the span of all the vectors up until that point. So by the previous proposition, M of T is upper triangular with respect to this basis. Okay, so a lot of moving parts to this proof. I think this proof is not obvious. Like, I think there's some clever ideas here. I don't think it's very obvious to choose T minus lambda I, take the range of that, and then sort of expect to be able to get the basis by using that. Of course, once you see it, you can understand how it works. It does work. But probably, I mean, it's a cool technique, so you should study this proof. But it's maybe more important to remember the result, which is as long as you're over the complex numbers, you can always choose a basis such that the matrix of a linear operator is upper triangular, which is a highly non-obvious fact as well. Okay, but why would one want to do this? What's the benefit? What's the point? Okay, and the point is, if the matrix is nice, it can tell you properties about T. Maybe I shouldn't say the point. What's one point? Maybe there's maybe many points, but for example, if I just give you a general linear map by just giving you a matrix and I ask you, is it invertible? Your answer should be, I don't know yet. I need to row reduce it, right? If I just give you a random matrix, if I give you a random matrix, I guess the probability wanted should be invertible. But if I just give you a matrix with lots of non-zero entries and I ask you, is it invertible? Your answer should be, I don't know. If I give you a random matrix and I say, oh, what are the eigenvalues of this matrix? You should say, I don't know. in this class, you should really say, I don't know, because we haven't covered determinants yet. So you really don't know. On the other hand, if I give you an upper triangular matrix and I ask you, is it invertible? What are the eigenvalues? The answer is actually immediate. So if you've chosen a nice basis so that your linear map has a nice matrix, the matrix can tell you a lot about the linear map. Okay, so I won't prove this. I'm sort of just including this. I mean, it's in your book, but I'm sort of just including this as a why would you ever want to upper triangularize? So suppose that T is an upper triangular matrix, or has an upper triangular matrix. Okay, so remember, this is always possible if the field is C, but it's not necessarily always possible if the field is R. Then, so two things you could tell just by looking at the matrix. So T is invertible if and only if all the diagonal entries are non-zero in this upper triangular matrix. Second thing is the eigenvalues of T. These are just equal to the diagonal entries of M of T. Okay, so if I give you some huge matrix, 1, 7, 0, 3, some stuff over here, zeros here, and I ask you, is this matrix invertible? You say, oh no, zero is an eigenvalue. Therefore, it's not invertible. Whereas if I give you a different matrix, 1, 7, 0, 3, but then I just put a bunch of crap here and a bunch of crap here, and I ask you, is this matrix invertible? You say, I don't know. Unless I ask you on a homework exercise, in which case you should figure it out for me. Okay. Anyway, so this actually covers both 5B and 5C. I know it was kind of quick. What I try to do is I try to condense the two sections in a parallel way. Right, defining diagonal and upper triangular at the same time. So we went through this a little bit quickly. Which means that actually already we're ready to start chapter 6. Okay, but I'm going to want to take maybe more time in chapter 6 because I think it's going to be more new. And then chapter 7, we'll see how far we can get, I guess. I guess the syllabus says we're trying to cover chapters 1 through 7. And how much time do we have left? It's like, it's about 3 full weeks. We may be able to cover a decent amount of chapters 6 and chapter 7. So next time, 6A, which should be sort of very new. Okay.